In this example, we are given a list of 3 premises or statements, and we want to try to draw any conclusions possible and state which rules of inference we use to obtain those conclusions. So let's start by unpacking the first statement here. This says that every, so this is going to end up being some kind of universal quantifier. So every computer science major has a computer. Alright, so I'm writing it like this because this is actually an implication, right? It says if a student is a computer science major, then they have a computer. And we can write this out in the following way. We can define propositional functions. Let's say P of X we can define to be X is a CS major. So then this statement right here says P of X, right? And then we can define Q of X to be X has a computer. So these are propositional functions. Now, X has a computer, and at this point our statement says for all X, and then P of X, so if our student is a computer science major, P of X implies Q of X, then they have a computer. So I'm getting real serious with the color coding here, but for all X, P of X implies Q of X. Now, what do the other 2 statements say? Well, these are instances, right? These are instances of the second propositional function that we made, the propositional function Q. The first one says Ralph does not have a computer, right? So the next argument here, I'll do this in 2 separate, these are going to be 2 separate statements here, but the second statement here is Ralph does not have a computer. Well, have a computer, that's our propositional function Q. It's got to be the negation because he does not have a computer, and then we just plug in Ralph for X. So we have not Q of Ralph. All right, and so can we make any conclusion here? So remember, in our logical argument notation, when we stack these up like this, these are conjunctions together, right? So we know that for all X, P of X implies Q of X, and we know not Q of X. Well, this is an example of universal modus tollens, or universal indirect reasoning, right? And the conclusion then, based on that mode of reasoning, or that rule of inference, is that not P of Ralph must be true, right? So we can conclude not P of Ralph, and this is done by universal modus tollens, however you want to pronounce that, but that's by universal modus tollens. And not P of Ralph means what? Well, if Ralph does not have a computer, then Ralph is not a computer science major, right? So Ralph is not a CS major. That's our conclusion in plain English, right? But this is our logical argument set up right here. So let's look at the situation with and now, and see what we can say about that. So I'll just start another argument down here. Copy the part that's going to be a repeat. The universal part is the same, right? But now what are we told? We're told that Anne does have a computer. So Anne having a computer can be written as Q of Anne. It's no longer negated because Anne does have the computer. So can we draw any conclusions from this? All right, so we have for all X, P of X implies Q of X, and we know Q of Anne. Can we say anything about P of Anne? And the answer is no, because this statement will be true if you have P of X implies true. Well, true implies true and false implies true are both true, right? Those are both true statements. And so this one it leads to no conclusion, at least in terms of Anne being a CS major. Anne could be a CS major, or maybe Anne's not a CS major, and we cannot conclude given the information that we have. So our conclusion here is that we don't learn anything about Anne's major, but we know for sure that Ralph is not a CS major.